Since its creation, the Earth has never stopped changing. Colossal forces have hurled ocean floors upwards and made them into towering mountain ranges. Incredible collisions have created entire continents. These tectonic forces are still at work today. We see them in volcanic eruptions, earthquakes, and tsunamis. Tectonics sculpt our landscapes, change our climates, dry up our oceans, and can destroy life. Asia is a continent on high alert, and scientists are watching it closely. The greatest tectonic cataclysm in history, Asia's collision with India, still threatens Nepal, the Tibetan Plateau, and China. Japan, shaken by tremors every day, could see the very symbol of the country erupt in the near future. In Indonesia, volcanic activity is both a danger and a resource used by people who put their lives at risk. These incredible phenomena are the result of the never-ending voyage of the continents. The building of the Asian continent took billions of years. It started with Siberia, but then added huge land masses like Mongolia and China. More recently, India collided with the south of Asia, giving birth to the towering Himalayas. These cataclysms created a continent that is both immense and fragile, a world teeming with life. But putting together the pieces of Asia didn't mean the continent would be either stable or unchanging. Asia rests on tectonic plates that are still active. They push into each other, separate, and collide. At this very moment, the Indian plate continues to dig right into its Asian neighbor. This mammoth and uncontrollable event is about to cause a catastrophe in Nepal, a tiny country wedged between India and the rest of the continent. Some scientists believe that this peaceful landscape is concealing a colossal energy that's about to cause a major earthquake. Seismologist Christelle Chenard is working in a remote area northwest of Kathmandu. Christelle's job is to monitor seismological stations in Nepal, make sure everything's working properly, and to gather the valuable data that's been recorded. The researchers have to go far off the beaten path to get to the many strategically placed GPS stations. The recorded data will help them understand what is happening below Nepal's surface.
A point just below the antenna shows us that every year the Himalayas move 2 to 4 centimeters. It doesn't seem like much, but it is 1 meter per human lifetime. In terms of millions of years, this is enormous. This is one of the fastest moving places on the planet.
When the underground tensions become too great, there will inevitably be a release of energy and the ground will split apart. Nepal's last major earthquake occurred more than 300 years ago. That's a 300-year buildup of tectonic energy waiting to be released. The threat to Kathmandu, the country's largest city, is growing closer.
We are in Asan, one of the most densely populated parts of Kathmandu. There hasn't been a major earthquake in western Nepal for almost 500 years, and we're expecting one soon. Although everyone knows there is a high risk of earthquakes in Nepal, all the buildings have very weak foundations, and they're being built higher than ever. Besides that, we're situated on a sedimentary basin, so the foundations are not well anchored, and the ground is very movable. If a major earthquake occurred anywhere in Nepal, the consequences for a neighborhood like this one would be terrible.
The tectonic pressure of the Indian plate threatens more than Nepal. Further north, in western China, another network of faults splits the continent. This fragile zone, the Tibetan Plateau, has on its northern borders a mountain chain parallel to the Himalayas. They're called the Kunlun Mountains. These mountains form a 3,000-kilometer geological barrier that is resisting the movement of the Indian plate. They are literally keeping China from being pushed northward. It's the Tibetan Plateau that's doing the heavy work of absorbing the impact of the Indian plate. At the foot of the mountains, researcher Jan Klinger drives toward the gigantic fissure that is continually reshaping Tibet, the Kunlun Fault.
Here we're really on the fault. This topography we see reflects the long-term action of the fault. We see these broad surfaces that accumulate movement, with the Tibetan block moving slowly, just 1 centimeter a year, relative to Eurasia to the north. So this whole block is being lifted up in reaction to the India-Asia collision much farther south.
The Indian tectonic plate is so powerful that it's actually pushing Tibet up against the Kunlun Mountains. It's also pushing the whole Tibetan Plateau and part of China to the east along the Kunlun Fault. This movement doesn't always happen quietly. Occasionally, the tectonic energy pushes to the surface with dramatic results.
The fault itself is blocked, so there's no continuous movement. The tension builds up and then is released in frequent major earthquakes. The most recent one happened in 2001. That was a 7.8 magnitude quake whose effects are still clearly visible today. Here we are looking at the effect of the 2001 earthquake. That horizontal split cutting through the hill. The earthquake shifted those little channels on the hill out of line, with the landscape moving in opposite directions. Here on the fault line, they don't join up. To follow the trace of this channel, we have to walk 4 or 5 meters further along.
It's hard to imagine the amount of force needed to bring about such movements of the Earth's crust. Luckily, this earthquake occurred in an uninhabited region. However, it's graphic evidence of how, over the last 40,000 years, tectonics have moved huge amounts of ground, hundreds of meters. The large faults of the Tibetan Plateau have affected the geography of Asia, sometimes in spectacular ways. A few hundred kilometers away, in Inner Mongolia, the Baden-Jaran Desert owes its unique appearance to the tectonics of Tibet and the Kunlun Mountains. These dunes are part of the highest desert in the world. Their crests are over 500 meters high. Unlike the dunes of the Sahara, which are sculpted by the wind, the Baden-Jaran dunes are unchangeable. Even more surprising are the 75 permanent lakes that adorn the base of the dunes. Their existence has long been a puzzle to scientists. For dozens of years now, Chinese geologists like Professor Ji Baodong of the University of Beijing have been trying to solve the mystery of these desert lakes. Professor Dong starts his latest investigation at about 30 meters above the lakes.
Here, the surface of the sand is dry. But if we dig down, we may get a surprise. And sure enough, the underlying sand is wet. This indicates there is water in the dunes. Researchers believe this water, which also feeds the nearby lakes, comes from north of the Kunlun mountain chain, arriving via a network of deep faults.
The water that fills these odd desert lakes comes from under the ground. It flows down the slopes of the Kunlun Mountains, seeps through underground faults, and finally re-emerges hundreds of kilometers away. But what accounts for the interior of the dunes being humid? Scientists think the answer has to do with tectonics. Hundreds of kilometers underground, tectonic plates are pushing against each other along fault lines, creating intense heat and volcanic activity. The most commonly held theory is that this underground furnace heats up the groundwater as it moves along the faults below the desert. Some of the water evaporates and steams up into the dunes of the Badinjaran. The lakes at the base of the dunes have a high mineral content, an ideal environment, supporting vast insect colonies and a diversified fauna. But the fault networks do more than irrigate northern China. Unfortunately, they also have catastrophic consequences. 500 kilometers from the desert, running along the eastern border of the Tibetan Plateau, another network of faults has ravaged the landscape. A major fault, the Sichuan, tore through this land, lifting up the ground and releasing a monumental amount of energy in a few seconds. It was May 12, 2008. An earthquake that registered 8 on the Richter scale devastated Sichuan. It wiped out a city of 20,000 people, cut mountains, villages, and houses in two, and caused over 70,000 deaths. Back in the 1970s, Cold War tensions resulted in the Chinese government building several factories in this secluded mountainous region. At that time, there were no records of previous earthquakes in this area. Planners were unaware that they were building right in the heart of one of the most earthquake-prone regions of the planet. Xiao Qingji is a Chinese-Canadian professor of tectonophysics and geology at the École Polytechnique de Montréal.
This factory, built in the 1970s, produced sulfuric acid, and now this is all that remains. It's all very tragic.
In the aftermath of the 2008 quake, huge quantities of sulfuric acid spread over this site. The corrosion can be seen everywhere. Many workers died in this quake. Xiao Chengji arrives at a railway line that used to service the acid factory.
This railway bridge was completely destroyed in the earthquake. The upper part of the mountain behind me was totally shaken apart, and huge boulders came crashing down the slope.
But the worst damage happened to the buildings that were constructed directly above the fault. This ruined building used to be a hotel that straddled the frontier between two small tectonic plates.
A magnitude 8 earthquake like the one that happened here releases a tremendous amount of energy. At the bottom of the valley on my left, a large fault caused all the ground to sink. But here, under my feet, we have the main fault, where all the stress bottled up in the earth was released at once. This section used to be level, but now you can see it slopes at a 30-degree angle at least. Incredibly, there's now a 4-meter difference in height between the upper and lower parts. And the astonishing thing is that this applies throughout the region. A vast territory was instantaneously lifted 4.5 meters by the earthquake. Over there, they're putting up new buildings less than 50 meters from the fault. It's extremely dangerous. If another earthquake happens, there's a good chance that it will all collapse again. Look at the materials they're using. This skinny rebar, it's no thicker than my little finger. And the cement blocks only have 4 rebars each. They need much thicker ones. And look at these bricks. They're poor quality. See? They're already cracked.
Though the Chinese authorities may be slow to impose stricter construction standards in the region, they are investing in research. In the wake of the earthquake, the Chinese scientific community is trying to deal with the permanent tectonic threat that hangs over the region. Professor Haibin Li from the Chinese Geosciences Academy takes Xiao Chengji to a site unique in the world. Teams work here day and night, hoping to extract precious knowledge buried deep in the earth. The equipment they're using is normally employed in the search for minerals or oil. In this case, they're drilling non-stop several hundred meters down, hoping to understand what's happening in the fault responsible for the devastating 2008 earthquake. The rock sample, or core, is a little over 2 meters long and was extracted from a depth of 2 kilometers below the Earth's surface. Coming from that depth, this is a very valuable piece of information, a kind of 3D X-ray of the fault as it is right now.
There are fissures in this exact spot. A small earthquake started right here.
The idea behind drilling the first well was to take samples from the fault. Later, a second well was dug above the fault. Next, the scientists will inject fluids into one of the wells. A sensor and a seismometer at the base of the second well will show whether the fluid is being transferred all along the fault. If the fluids move quickly, it shows that the fault is flexible and the earthquake risk is slight. If the fluids have difficulty reaching the second well, it means the fault is closing and dangerous tectonic tensions are starting to build up again. At this rate, China is destined to become a world leader in earthquake prevention, especially in understanding the tectonic forces that so deeply affect their own country. In Japan, scientists have studied the effects of tectonics for decades. Their country is situated in the Earth's most unstable region. For hundreds of millions of years, Japan was attached to the eastern coast of the Asian continent. Then, about 15 million years ago, the subducting plates of the Pacific pulled Japan eastward, opening up the Sea of Japan. The entire country sits atop the meeting point of the Pacific, Filipino, and Asian plates. This earthquake and volcano zone is known as the Pacific Ring of Fire. From time immemorial, the Japanese people have had to adapt to the instability of the earth beneath their feet. In the vast megalopolis of Tokyo, almost 35 million people are crowded into one of the most fragile zones of the Earth's crust. Because of this, the city's buildings are designed to withstand the most violent tremors. At the University of Tokyo, Professor Takashi Furumura has created computer simulations essential for the safety of Japan.
It's still difficult to predict exactly when an earthquake will occur. But with all this, we can estimate the likely force of its vibration and the extent of the damage. I think this is important in a country like ours.
These simulations are produced by one of the most powerful computers in the world. At the Yokohama City Earthquake Information Center, scientists are keeping a very close eye on Japan's daily tectonic upheavals. Tens of thousands of earthquakes are registered every year, but even the most advanced technology and the best construction techniques aren't enough to protect Japan from nature's most destructive outbursts. In March 2011, a magnitude 9 earthquake set off the most devastating tsunami in the country's history. As if earthquakes weren't bad enough, Japan is also threatened by frequent volcanic eruptions. the country is sitting on a geological powder keg. Underneath the country, the Pacific plate is sinking under the weight of the Asian plate. The resulting subduction has created the Izu Archipelago, a volcanic arc of explosive islands. The most famous of Japanese volcanoes is Mount Fuji, formed several 100,000 years ago. Fuji has erupted dozens of times, and each lava flow has lifted the mountain higher. At present, it towers more than 3,700 meters over Japan. Despite its peaceful appearance, many scientists believe that Mount Fuji poses a major risk for the entire southeastern part of Japan. Volcanology researchers Takayuki Kaneko, Takao Ominato, and Taketo Shimano of the universities of Tokyo and Fuji Tokoha are heading out into what they call the Grand Canyon of Mount Fuji. The three scientists are standing on a lava flow that was expelled during the last eruption back in 1707. Today, they're taking samples. The researchers believe that the core of Mount Fuji is fed by magmas of different types, one of which is particularly explosive.
We think these rocks may contain droplets of andesitic magma. This would mean there is not just one magma chamber under the volcano, but two. The problem is, the andesitic magma from this second chamber explodes when an eruption occurs. We believe Fuji spews a mixture of matter issuing from two separate chambers. Normally, the magma comes mostly from the lower chamber. It isn't very dangerous since it's classic basalt lava. But the more magma there is from the upper chamber, the more explosive the mixture becomes. It can produce very violent eruptions.
The andesitic magma could produce significant pyroclastic flows on Mount Fuji. When the plume that shoots out from a volcanic explosion loses momentum, the falling matter can cover the entire mountain. It's horrible. Burning magma mixed with deadly gases rushed down the slope at more than 100 kilometers an hour. Until now, scientists thought Mount Fuji was mainly a basaltic volcano, and therefore, that the risk of an explosion was low. But we've recently discovered evidence of many pyroclastic flows on Fuji.
Volcanologists studying Mount Fuji foresee the likelihood of an eruption in the next few years. The volcanism of the Pacific Ring of Fire is at its most dangerous on the island of Java in Indonesia. There are at least 20 active volcanoes on the island. Among the most famous are Bromo and Semeru, both of which threaten to erupt at any moment. It's a wonderful place for those who study volcanoes. Anthony Williams-Jones and his son Glenn are Canadian researchers who study Indonesia's volcanoes. Right now, they want to get samples from one of the most active Indonesian volcanoes, Kawa Ijen.
This is really, truly a phenomenal location, which hosts the world's largest, most hyperacid lake. It has a pH of 0, so it's as strong as any car battery acid. We see this beautiful blue lake. We'd just love to go for a swim, but not a good idea.
Father and son are on the verge of proving a theory that could revolutionize our understanding of how volcanoes work. But this is a very dangerous business.
These are all layers of what we call pyroclastic material. Effectively, this is an explosive volcano, highly explosive. We call it a stratovolcano.
To do their research, Anthony and Glenn expose themselves to deadly levels of sulfur dioxide, hydrogen sulfide, and hydrochloric acid.
Yeah, I'm afraid we're going to have to put on our gas mask now.
Yeah.
I got mine all tangled.
Now we can breathe. All right, clearing a little bit. As we see, the wind has dropped and the gas is staying locked down in the crater. But you can imagine being a miner and going through these conditions every day.
A sulfur mine has been in operation since 1759. A natural dome has been hollowed out to collect the extremely toxic gases, which then condense into sulfur. In earlier times, these gases were harnessed to produce gunpowder. Today, workers are risking their lives to obtain sulfur whose only use is to turn brown sugar white. With practically no protection, the miners work for about $15 a day. This is 3 times the average salary in the region, but very few of them live past the age of 50. The researchers believe that Kawa Ijen might be able to produce something much more valuable than sulfur: gold.
So we're measuring water vapor.
This bold hypothesis depends on an analysis of the chemical composition of the gases wafting out of the dome.
Oh, it's spiking. We got good. That's great. The gas blew into the sensor.
Very, very nice.
And here it's gone off scale. Oh, look. Yeah, there we are. We've got a nice spike. Everything's rising, so plume has moved in.
This is really good news. One of the reasons that we're actually measuring hydrochloric acid is it turns out that gold will complex with the chlorine in the hydrochloric acids. Normally, you can't dissolve gold, but we have been able to show experimentally that when we have it in the presence of hydrochloric acid, we form a big, fat, ugly molecule that is very, very volatile. This means that gold will be able to move in the vapor to some place where it'll eventually get deposited.
Maybe we're getting that gold transport.
It's
Here,
off scale, obviously.
It's off scale.
According to our 2 researchers, the toxic blasts of Kawa Ijen carry gold in its gaseous form. This gold would have formed hundreds of kilometers underground, down where the archipelago's tectonic plates converge. The concentration of hydrochloric acid produced by the volcano appears to be high enough for our modern-day alchemists to proceed to the second stage of their research, one that's even more dangerous. They want to obtain a pure sample of gas from the very top of the volcano's dome. Only samples taken directly from little holes in the dome are valid for analysis, since they will not have been altered by contact with the surrounding air.
What we'd like to see is some fairly high temperature fumaroles, perhaps of the order of 400, 500, 600 degrees Celsius. You've got to be really careful here. We're starting to get blasts of heat at us. From time to time, you'll see a little red flame. That tells me that is very high temperature. So this is pretty exciting. It's just a matter of trying to get into the right position. 290, 300, 310. Okay.
More than 300 degrees Celsius. Now they have to put a titanium tube right into the volcano. Titanium is the only material that can resist the corrosive heat of these gases.
And I've got flow. I'm filling it up. It's getting really hot. We're getting blasted. Blasted by hot gas from below us. It's got to turn on us because the slope. Because it's just getting way too hot.
Now they must condense the gas to get a liquid sample for analysis in the lab.
Maybe here at Kawa Ijen, we have a baby gold mine that is forming as we watch it.
Anthony and Glenn move to the north wall of Kawa Ijen, on to what's left of the remains of the last major eruption that occurred 200 years ago. If their theory is correct, the volcano should have deposited small amounts of gold during its most recent eruptions. Anthony explains how gold vapor could have ended up on the rocks of Kawa Ijen.
We can see all of these veins. The water that has condensed, we've simply cooled down the gases. The gases turn into liquid. They move in and they open up these fractures and they deposit minerals.
The next step is to take a sample from a pyrite vein to see if it contains traces of gold.
And I'll just break off a piece here. And here's a piece of the pyrite vein. And we're going to take it back to the laboratory. We're going to analyze it chemically, and we're going to look for the gold in that pyrite. And this is really important because until now, yes, we've known this type of alteration is associated with gold deposits, but no one has ever seen a gold deposit really in the state of formation. We know this one, if it is a gold deposit, was forming 200 years ago, and we know that the same thing is very probably happening below the active dome. Well, it's hard to believe that just a few hours ago this morning, we were within 2 or 3 meters of that bright blue flame that you can see now. The blue color that you can see is the blue color of sulfur. But I think we'd be dishonest if we didn't say that we're attracted by the adventure. We're seeing nature at its most powerful. At a more fundamental level, of course, we want to understand the nature of this power. What is it that creates a volcano like this?
The lives of Indonesians are affected by more than just powerful volcanoes like Kawa Ijen. Geology has often been a matter of life and death for the peoples who came to this land. The island of Java is full of astounding archaeological sites. Over the years, an impressive number of plant and animal fossils have been unearthed. The most fascinating of all is the evidence of early human beings. Some skulls found here are very old. Others are much more recent. Their presence in this remote island chain is startling. How did these primitive people end up in an isolated territory hundreds of kilometers from continental Asia? In the village of Pakatan, scientists from many disciplines work together to solve this mystery. They are trying to map the history of humans on Java, a history which began almost 2 million years ago.
Look at this.
Francois Sama, an archaeologist, believes that understanding human history in Indonesia will come from studying how the geography of the islands has changed over time. In 1891, a Homo erectus skull was discovered on Java by Dutch paleoanthropologist Eugene Dubois. It was the oldest human skull ever found outside Europe. Its age, over 1.5 million years. Francois has continued in the tradition of Dubois, working in places which have now been classified UNESCO World Heritage Sites. Here, in the Song Terrace Cave, his team has made many discoveries that have helped us understand how Homo erectus might have reached Java.
In this region of Southeast Asia, we find the first island dwellers in the history of humanity. They didn't get to the islands by boat. They crossed over when sea levels dropped during one of several ice ages that have occurred in the past 2.5 million years.
Ancient humans came to Java thanks to a global cooling period that turned much of the planet's water into ice and concentrated it at the two poles. With the water level vastly lower, human beings were able to cross to Java on foot. But in the warming period that followed, the sea rose spectacularly.
Suddenly, within a few million years, the sea rose by more than 125 meters. Thus, a continent crisscrossed with valleys, where people lived and had spread out, became an archipelago.
Homo erectus was trapped on the islands of the Indonesian archipelago. At Song Terrace, the researchers found a Homo sapiens skull that's about 40,000 years old. Analysis has shown that this Homo sapiens is not descended from Homo erectus, but he arrived in Java the same way, taking advantage of the drop in sea levels, this time from a later ice age. The researchers believe that, in fact, this type of migration of prehistoric populations happened repeatedly over the past 2 million years. Near Song Terrace, Francois Sermat continues his research in a cave carved out by an underground river. This cave is composed of limestone, which dissolves easily in water, which means that caves like this can be formed relatively quickly, and the bodies of water that dig them out sometimes contain surprising archaeological treasures.
The great thing is that the river behaved almost like an archaeologist working in reverse. We can see in this layer of hardened clay the underside of all the rocks it contained. And here, stuck in the roof, are these tools of prehistoric man. Their cutting edges are still sharp. And here's a little flint chip fashioned by man in extraordinarily fresh condition. It's like new.
Over time and throughout the ice ages, caves served as shelters for innumerable groups of people. In southern China, a whole village was built in the cave of Zongdong, which translates as the Middle Cave. Located in Guizhou province, less than 300 kilometers from Vietnam, Zongdong is a gigantic natural cave dug out by water and wind and lifted by tectonic forces. Zongdong has a population of close to 100 people of the Miao ethnic group, and a primary school with 200 pupils, some of whom walk there from surrounding villages. The cave is about as big as an airplane hangar. Inside the cave, erosion has hollowed out little craters that now riddle the ceiling and walls. People make their homes out of woven bamboo. And if the stalactites occasionally drip, it's no problem. The villagers just use the water. And the homes need no roofs. They already have the protection of the cave's limestone ceiling. Zongdong is evidence that the Earth's powerful forces are not always destructive. They can also give humans the shelter they need. Hundreds of kilometers from Zongdong, geologist Sylvie Crascan and her colleagues are exploring a network of caves carved out by the Li River. Caves formed in a tropical climate sometimes take astonishing shapes. Here, gigantic pieces of rock seem as if they might fall at any moment.
We're discovering absolutely fantastic caves. The walls are limestone. The rock is between 300 million and 280 million years old. Here in this cave, the river is very high, and in fact, we're up near the cave roof. We can see fabulous stalactites in the most extraordinary shapes. It is simply wonderful.